So let's start off again with something that we're a little bit more familiar with, and that is a particle traveling along, and it's going to travel a certain distance, and we can time how long this takes. And so we can plot the distance traveled, and I'm going to say that that's along the x direction, and along this axis we're going to have time. And so let's say it's a straight line again, and if we were to work out what the velocity was, we know that the velocity is the distance divided by time, and in this case that's x over t. Now if we look at the function we had before, f of t, f of x, but I'll change it to f of, I'll go to f of x first. The function we had before, which was this here, and this is similar to what we've got here, except that our variable in this case is t, and so we just have to replace it like that. And we note that the slope of the line is our m value, and we can find that from any 2 points, as we found earlier. And you'll find that if we want to calculate m, we would go the change in x divided by the change in t over any 2 points, and that's actually the velocity. And so this equation is actually f of t is equal to v times t. And so we find that the slope of this line here, the slope is the velocity, which is really quite cool. So let's now plot the velocity as a function of time. Now if we choose any 2 points along here, we'll actually find the same velocity because it's a line. And so the velocity will be at some fixed value, and it will stay at that fixed value for the whole duration of the time. And so, sorry, that's not quite straight. So this here is the velocity as a function of time. Now let's just call this v1, for example, and the slope of this line is going to be v1. And what we notice is that we can rearrange the equation v equals x over t, and we can rearrange it for x. And so x is going to be equal, if we times both sides by t, t's cancel, and we've got v times t, which is actually what we've got up there. So we find that if we want to work out the distance travelled over a certain amount of time, we just have to multiply this v1, which is the height here, by the time it takes. Let's say that's t1. And so x1 would then be equal to v1 times t1. And you can just think of this as the area under the graph, this area here. And so if we want to find out the distance travelled, we have to find out the area under this plot. And so going from this step to this step, we call this differentiation, and that's finding the slope at all points along the graph, and integration is the inverse. Integration. And the way I think of this is summing up all of the different elements and working out the area under this graph here. And this is simple for a line, so this is simple for a line, but it's more difficult if we have a function. And so let's think about how we could find the slope of all the points along a line. So sorry about all this noise. So let's think about this parabola here. So that's a terrible parabola, but you get the idea. And we want to find out the slope at each of these different points. Let's say that this is also an x versus t graph. And so one way we can think about doing that is we can think about taking segments along this line and finding the slope at each of those points. And so we're going to have a delta x here, and a delta t, a delta x, and a delta t, a delta x, a delta t. And for each of those points, we can plot a corresponding value for the slope at those points. So that would be this here would be the slope of that line, this segment. Then we'd have like that there, and for this part here we'd be calculating this slope here, and so that would be this here, and you could keep going, and for a parabola you'd actually find a line. So mathematicians have found a way of explaining this or calculating this using what's called limits. So limits are kind of similar to what we covered in series, where you can have where you can take a variable and you can see what happens to the rest of the function as you move that towards another value. So I'll give you an example. So if we were to think about one of these segments here, okay, and we're just going to make that a bit larger, and so we want to find the slope of the tangent line, and that's the line that is parallel to the small line section just at this point here. So slope of the tangent, and so let's zoom up on that again. And so what we'll have is this line, and then we'll kind of have this curved section, and we want to find the slope at this particular point. And so let's call the function's value, or its y value, f of x, and let's say that we want to consider a point that is a distance h along this direction here. And so what we have to do is we have to take the function and we have to add to the x value some value h. And the idea here is that what we're trying to do is we're trying to find the rise over the run, and then we're going to see what happens as our h value goes towards 0. And the idea of this is that these little small sections here are getting smaller and smaller. So the area, the distance over which we calculate this slope is getting smaller and smaller. Alright, so we can calculate the rise. The rise is just going to be f of x plus h minus f of x, and the run is going to be just simply h. And so what we want to calculate now is we want to calculate what's called the limit as h approaches 0. So that's as this goes incredibly small. So we're thinking of smaller and smaller and smaller little sections that we're going to calculate the slope over. And it's the limit of the rise over the run, which is f of x plus h minus f of x divided by h. And we can actually calculate this. So let me calculate it for a line. So let's just say that the function as a function of x is going to be mx plus c. So this is common, we've seen this before. This is the function for a line where this is our y-intercept. And then this here is our slope. Alright, so we just basically put in the values. for this part here, we have to replace x with x plus h. So we have the limit as h tends towards 0, and f of x plus h is going to be m, and we're going to replace x with x plus h plus c, and then this here is going to be minus f of x, which is just mx plus c. And we're going to divide that by h. And so if we times this bit out here, what we're going to get is mx plus mh plus c, and we're going to get minus mx minus c. And we see that the c's cancel, the mx's cancel, and we're left with mh over h, and we also see that the h's cancel. And so the limit as h goes towards 0, there's actually no h in this form, so the limit of the slope of this line is just going to be m, which is what we know. So this is actually the kind of a rough proof for the fact that m is the slope. And we call this f dash of x, or we can also say df dx.